In our next example, example 9.3, we're going to compare two savings accounts for two coworkers. As the problem indicates, both women made identical contributions, $410 each quarter, to their retirement savings account. Both women invested for 20 years, but the distinction is that Madison made these investments from age 25 to age 45 and then let the amount in her balance just sit and continue accruing interest. Kennedy, in contrast, didn't start investing until age 45, and so she only invested in her account from age 45 to age 65. Let's start with Kennedy's calculation. We'll use the savings formula. We know her PMT is 410, APR 0.052. I'm using n equals 4 since interest is compounded quarterly, that is 4 times each year, and a capital Y for 20 years. Plugging these into my formula yields a value of $57,094.68. So when Kennedy hits age 65, that's the amount she'll have in her savings account. Madison will have made the exact same investments from age 25 to age 45. So at age 45, she'll have the same amount that we just calculated that Kennedy will have at age 65. At age 45, Madison stops making investments into her retirement account, but the money continues to earn interest. So we can treat the balance that she has at age 45 as a one-time investment. Think about if she had just showed up to the bank on her 45th birthday and made a one-time deposit of $57,094.68. So for the second 20 years, in Madison's context, specifically from age 45 to age 65, we'll be using the compound interest formula. Plugging the values in as necessary, we find that when she turns 65, she'll have $160,454.26. It's valuable to note that both Madison and Kennedy invested the exact same amount of money. So how did Madison end up with almost 3 times as much? Madison made her investments early, and so from age 45 to age 65, she didn't have to continue investing, but interest was still building or accruing on the balance that she had. Underneath example 9.3, there's a short paragraph that points out that anytime we borrow money and pay it back through regular payments, say if you borrow money to buy a car and you make monthly payments, or if you borrow money to buy a house, that is, you get a mortgage and you send in your monthly mortgage payment. In any context that has that structure, the payment that you send in gets divvied up between interest to the lender and a payment towards the loan. The next example demonstrates this process. We're told that Shelby and her husband borrowed $210,000 to purchase a home. The home loan had an APR of 5.25%, which was compounded monthly. It was a 30-year loan, and based on these terms, their monthly mortgage came out to be $1,159.63. If you think about the common structure of a loan problem, we've actually been given all of the variable values. There's nothing to solve for. So unlike most loan examples, the purpose of this example is not to calculate a monthly payment or a total amount that they pay on the loan, but instead to try to understand what happens when they send in their monthly payment. Take a second to copy down this table that we'll use to track exactly what happens to the monthly payment that they send in. As indicated in the problem, we'll just track this payment over the first 2 months. Month 0 can be thought of as when they just finished signing the paperwork, just get the keys to the house. They haven't made any payments yet, and we know that their overall balance is their original loan amount of $210,000. In months 1 and 2, we already know how much they're going to send in for a payment, specifically $1,159.63. If we wanted to calculate the balance after their first month payment, it's tempting to think we simply subtract $1,159.63 off of their current balance of $210,000, but it's more complicated than that. And the purpose of this problem is try to understand exactly how that payment gets split up. The first thing we'll do is to determine how much of their payment goes to interest. In any given month, the amount of a payment that goes directly to interest is calculated by taking the balance the current balance, the balance from the previous month, and multiplying by the monthly interest rate. In month 1, when Shelby and her husband send in $1,159.63, the first thing the bank is going to do is take their current balance, which is the full loan amount, $210,000, and multiply by their monthly interest rate. Notice that I've taken the annual rate of 5.25% or 0.0525, and I've divided by 12 to get a monthly rate. This comes out to be $918.75. So I can put that value in my table. Next, to determine how much of their payment goes to principal, we take their total payment, $1,159.63, and we subtract off the value that we just calculated. That value we just calculated, $918.75, is going directly to the bank. They just keep that. That goes towards interest. So the remaining $240.88 is all that goes to pay off the principal. So to calculate our new balance after our first monthly payment, we take our previous balance, $210,000, but all we get to subtract off is the $240.88 that is actually going to principal. Doing that calculation indicates that our new balance is $209,759.12. At first, it may seem like we've done the calculations wrong. How is it possible that we sent in a payment of over $1,000 and yet our balance is only about $200 less? The cruel reality is this is the nature of mortgages. This is the nature of any loan that you pay back through payments. A major portion of your payment is going to go directly to interest, and typically only a small amount will initially go to pay off the balance. Performing similar calculations for month 2 yields the values that you see. An important thing to note is that in the second month, the balance from the previous month is a little bit smaller, so the amount of money that we paid to interest is a little bit smaller. It's about $10 less. In month 1, I paid $918.75 to interest. In month 2, I only paid $908.96 to interest. This means that the amount that goes to principal will increase by about $10. And it's the nature of these types of loans that slowly but surely the balance between the amount to interest and the amount to principal shifts. So eventually you end up paying off the loan. Hopefully these calculations feel like the type of thing that you could easily implement in a spreadsheet program, say Microsoft Excel. Hopefully you can imagine yourself saying this next value will equal a previous value times some formula or some constant. And in fact, project 3 is going to require you to build a table such as this one, but actually build the entire table for the entire 30-year loan. So hopefully you understand the structure of the calculations that we've demonstrated in this example.